The basis of my 3D printed indestructible TPU quadcopter frame was this big quadcopter right here. This is a 24-inch between rotors, about 600 millimeters, and it's very large, printed in PLA. This was a project I did a few years ago, and the idea was to build a super lightweight frame that could fly for an hour, which it did. The goal of the project was met, and it's a pretty straightforward design. The arms are 3D printed. You can see they have kind of an optimized shape to them. The body is a sandwich. There's a bottom piece and a top piece, and then there are screws which run all the way through the body, through the arm, and into the landing gear to hold the legs on. This was kind of my previous experience designing quadcopters. And I took this design and I scaled it down and I made a little tiny PLA quadcopter that looked about like this, sort of, about this shape. And it used little tiny motors, little tiny 3-inch props, and the goal was to just have a really long duration 700 powered, that's the lithium ion cell powered quadcopter that I could just buzz around for 30 minutes. And it actually worked pretty decent, but it was incredibly fragile and would smash and shatter. And that's when I started the path of reinforcing it and making it indestructible. Version 1 of the PLA frame was printed in PLA Pro, which is a impact-resistant PLA, and it's a relative term, and it was all printed as one piece, so there's no sandwiched body. The arms and the body were one piece, and the electronics, the single all-in-one control board, was dropped in the top, and then a top cover, which was also acted as a battery holder, was snapped over that, and I used little nickel strips to support the battery, to connect to the battery using magnets, kind of like some of the previous long-range 21700 and 18650 builds. That frame splintered very easily at the arm joints. Basically, the walls were peeling away from the infill and resulting in the arms becoming flexible and breaking. Version 2 of the 3D printed quadcopter frame was still printed in PLA, but I used a modifier to make the walls of the arms extend through the body. And this fixed the problem of the walls peeling away at the radius by the arms, peeling away from the infill. It totally solved that problem. However, the PLA still cracked, broke down, and failed simply due to the impact of crashing the quadcopter repeatedly. The actual way I did that modifier was really simple. It's simply a little plug which I designed in CAD, imported into the slicer as a modifier, and then I took that plug and I set it, I changed like the wall speed very slightly. And what that did is it didn't materially change any of the print settings, but the slicer treated it, the parts of the frame that were being modified by the modifier, even though those modifications were very slight, were treated as a different body. So the arms were basically printed as a separate body. And that is what tied the arms into the actual body of the quadcopter. And that technique is actually pretty effective, but as you will see, it kind of caught up with us later. So at this point, the PLA was simply not working. It was shattering. It was just smashing like the areas that held the motors, the tips of the arms, at the root of the arms that attached to the body. Everything was cracking, delaminating. I was using lots of hot glue, melting stuff back together. We were having a lot of fun, but it was definitely not an indestructible frame. Here I have half a dozen of these little TPU quadcopter frames, and we'll start with the original one right here. And this was actually really similar to my PLA frame, as in it just, the arms are attached to the body, it's open on the top, closed on the bottom, and I have some inserts that snap in that support the battery and hold the circuit board in. It does also feature the modifiers that make the arms poke through the wall and kind of make them a separate body, which actually worked super well. This was printed in Ninja Flex, which is an 85A TPU, and there were some serious concerns that it would not be stiff enough and that there'd be some serious dynamic vibrations and things during flight that would make it impossible to fly. That actually turned out to not be the case. It worked really well, and I used this TPU for actually a few versions of the frame before moving to a stiffer one for other reasons. Mostly because it actually works just as well, and it's easier to print with. So this one here had the battery on top, which is actually a major problem. And this brings up a couple issues I'd like to discuss. First of all is my motor orientation. You'll notice that all of my motors point downwards. Even on my latest frames, I have the motors pointing downwards. There's two reasons for this. Well, really three. I did that on my big frame because it's technically a little bit more efficient, and I wanted the arms to be in compression. I didn't want to be pulling against the layer lines. I wanted the motors to be pushing against the arms so I could keep my layer lines in compression. On these little tiny TPU frames, that's not really important anymore, but I continue to do it. It looks way better having the motors facing down. So this is an aesthetic decision. Motors facing up just look silly, facing down doesn't. So hey, it looks super awesome, so I'll go with it. The number 2 reason is actually a really important reason. This is really the primary reason, is that it protects the motor. So if your arms are facing up and you're in a crash, the quadcopter is orientated forward, the motor bell is subject basically to the full brunt of the impact. And that will result in damaged motor bells and bent shafts. I've actually seen motors that look like this because they were facing up. And so far, I've had 0 issues with motors being damaged through those failure modes because they're facing downwards and they are completely protected by the top of the arm right here. No matter how you hit it, you can't break the motor. It's much, much more effective than trying to put a little tab on the end or something. The third reason is that theoretically, downwards facing motors are more efficient because of the shape of the airflow moving in versus moving out and the speeds involved and everything. And you should be able to get a tiny bit more flight time facing down. I have no idea if this is really a factor I should be considering, or if it's a factor that should be considered because it might be insignificant, but hey, it's one of the reasons. So the motors facing down, those are the reasons behind it. Originally, I had the battery on the top instead of the bottom, and the same reasoning we just talked about with the motors applied here. The battery was on the top. It was subject to the full brunt of the impact. So I have quite a few 18650s, actually 21700s was what this one was running on. I moved to the 18650s afterwards, that are smashed pretty badly from hitting hard objects. This particular original frame had these little PA12 rigid clips that snapped into the TPU body, and then there was a plate that came in on top of it. So the entire frame kind of had this internal skeleton of PA12 that kept the body rigid, and that really helped the torsion. You can see just a plain TPU frame with that insert removed is very, very, very flexible, which is not a good thing. But with that insert, which is what I continue to use that throughout my design, we'll talk about that in the next version, that insert really, really helps hold it together. So this particular one held up super well. We crashed it a ton of times, and it definitely needed some work with that battery mount. So then came in the next version. Next version was kind of a wonky one. I was trying to figure out, this was the biggest challenge, was mounting the battery. So this guy right here came up with this little solution for mounting the battery, which was similar to my original PLA version. And then I realized the battery needs to go on the belly. So this guy right here, I was trying to come up with a way of doing that. And I made this separate printed insert which has the battery holder in it, and it presses in from the top and gets glued in place. I actually just used hot glue on this guy. I was thinking and strongly considering sewing it in place with thread or on the edges, which actually might still have merit, but that's a very labor intensive. So the glue kind of worked. The problem is, because of all the overlap here, and actually all around the edges, the body ends up being a lot bigger than it needs to be, because there's a tab. You have to have a tab right there. You can kind of see it. There's a tab which is on this battery holder, which is what glues against the main body, and it adds basically distance. So this entire body is huge, which makes it heavier than it should be, which is a bad thing. Weight is a huge concern with these little guys, and we want to get it as low as possible to increase flight time. So this did, on the other hand, despite those issues, work really, really well. The battery retention was awesome. The battery was super well protected down in this little battery holder, and it held up quite well. So I ended up moving on to the next version, trying to help improve this little problem down here. And that's what you see right here. This is the first one I really actually used a lot, and it actually started suffering from some actual failures, which I'll get into, and we'll talk about how we fix those on the latest version. It has a new style of battery holder, which is similar to the last one, except this one is actually printed in place. So the way this works is we print the main body in this orientation right here, and then we flip it over, we print a PLA, basically a little pedestal in the print bed, pause the print, press the main body over the pedestal, swap to TPU, and then continue printing, resume, and basically print a TPU battery holder directly onto the belly of the quadcopter, which works really well. This one has some lamination issues, delamination issues. It didn't adhere that well, and I've had mixed results. The ones that do work really well. The ones that don't is basically due to environmental factors and not getting that first layer perfect. It's a really tricky process to get right, which is one reason I haven't released this quadcopter, is because I'm still trying to find a good solution to that. It's a great solution when it works, but it's finicky and definitely a high skill process that is difficult to get right and very, very not beginner friendly. So it is still the current method I'm using. And this kind of represents the final version of the quadcopter with many, many refinements. So I've done a lot of refinements, which we'll get to in a second. This did still have that insert, that rigid insert, which we can see in the latest version right there. This rigid insert is PA12 carbon fiber, and it basically reinforces the entire body. And works super well. The idea there is that the top of the arm is compressing the body. It's pushing inwards when the arm is pushed up, and the bottom is pulling out. So the bottom is just a TPU skin, which supports those tension forces, and then the top is rigid, which supports those compression forces. So it ends up with a really stiff arm, considering that it's made from rubber. The joint right here is very, very stiff and is not yielding. Now we've started having a failure mode, tearing. At the arm junction here, after enough impacts to the ground, the arm bending like this repeatedly on both sides, even on the back end actually, we got a tear forming right here at the front of the arm. Basically what was happening was, because I was extending the arm through the body, it was forming a stress riser. Every time the arm bent, it was straining the TPU rubber right at that point where the arm enters the body. Those two walls started straining, and a tear would form at the top, propagate down, and result in the arm being almost completely decapitated. As you can see here, the later version, the problem was persistent. I figured that the soft TPU might have a poor tear resistance, and I decided to move to a stiffer 95A TPU from Polymaker, which is what all the latest versions are made from. And that TPU was a lot easier to print with. For that reason alone, I'm going to continue using it for development reasons. It did not turn out to be any more durable than the 95A. Compared to the 85A Ninja Flex, it actually tore pretty much just as easily. And you can see this quadcopter frame here, which has hot glue on it because I just glued it back together. It has tears on both front arms and on both rear arms from various impact angles. And that's after a lot of crashes. This thing was flown quite a lot, and still held up decently except for those tearing. So that was a consistent issue we were suffering from. Also, this one here, the battery holder adhered super well, as you can see. Like, there is no peeling. This one worked really, really well, except at the front, where this little thin edge did not adhere well because it's difficult to maintain accurately the position of this camera mount when it's being set over that PLA pedestal. So we ended up getting rid of this layer on the latest version and just printing the battery holder without this aesthetic layer to add that little fillet to the front end. So moving on to what we tried next, and this, let me see. Actually, I grabbed these in the wrong order. These are actually two really similar frames. We did this one here first, and it started suffering from tearing, and as you can see, the top end is flat. I just added some improvements to the camera mount because protecting the camera is really important. This did not protect the camera sufficiently when you were running into like a steel gate or something. The TPU could bend enough that it would chip the lens still, so I added this little flared top, increased the camera angle for faster flying, and protected the camera better. So the latest version right here is the one where we actually kind of fixed all the problems as far as structurally. This is one so far has been basically indestructible. Now it is suffering from some delamination issues, if you can see that right there, for sure, because I ended up printing, when I printed the main frame, I flipped it over and I printed the battery holder in a room that was much too cold. We actually got kind of sucky layer adhesion. It's still holding up fine. The battery contacts are basically holding it on, and I think that'll work indefinitely, but not optimal. But the actual frame itself is in practically mint condition despite many, many crashes. To show you how this works with the modifiers, we're going to jump onto the computer and show you in the slicer. So we'll bring that up, and first I want to show you how my earlier modifier worked. You can see here, this is the finished result. You can see the arm, you can see how these outer walls kind of tuck through the body, and then on the inside you can see that seam there, and when we drag the lever down, you can see how the arm prints as an entirely separate body, basically, in practice. At the beginning it's not, and then it begins to be a separate body all the way up. And that is done via a modifier, this modifier right here. And the only thing I'm changing is the speed. I changed it from 30 to 29 millimeters per second. So this is a totally materially unimportant, completely irrelevant change, which doesn't matter at all as far as the print settings go. But what it does do is, because we are modifying the perimeters of the part, it separates into a separate body. And I want to show you one thing here, and that is with modifiers that affect the infill only, it actually does not affect the perimeters, only affects the infill. You can see that here. There's a modifier at the tip of the arm which changes the infill density underneath the motors, or above the motors, where the screws attach. And you can see how that infill is broken into separate bodies, how we have the low density over here and the high density over here, and there's a seam. There's two separate bodies. That's because we're only modifying the infill. If we had changed this to modify the perimeters would separate, come through here, and it would be extremely weak and break. But we're taking advantage of that property in the slicer to intentionally separate our arm into a separate body and have it slice it as such. And it ties it together and makes it a lot stronger and gets rid of that delamination of these perimeters from the infill, because it just ties it all together really well. Now, of course, the problem here was the stress riser, which would form right in here. The tear would begin at the top right here, where the top layer is really thin, because these layers in here kind of sag a bit, and they're not perfectly flat because they're basically overhang, and then they've got like one top layer which is intact, and that's not enough. So tear begins and then propagates. So let me show you how I fix that. Let's hop over into our other slicer. Other page open. You can see the outside. This is the latest version right here. The arm is completely streamlined. There is no seam there. However, on the inside, we have a seam. So what's going on here? I'm going to have to drag down and show you. And you'll see it's quite a bit more complicated right there than previously, and much more effective. So we've gotten rid of our stress riser. So we have this smooth surface out here. There is no seam, no line, no stress concentration. And then on the inside, we are reinforced with this reinforcing material right there. And what's basically happening is we're using a modifier, a very thin modifier, to take the inner wall and force it to make this long, skinny detour up along the arms wall and back in, and basically forming a stress reducer, basically a strain relief is what's being formed here. We're doing a strain relief. And you can see that strain relief continues all the way to the very top and reinforces that area that caused the tear to begin before at the very top. So it's kind of a fully holistic solution that adds almost no weight and completely solves the problem. Let me show you how we did that. We hop over here and you can see this kind of Gothic arch. This Gothic arch is basically a very, very, very thin modifier. If we select it, you can see I've added one perimeter. So this is doing a different thing. Previously, what we were trying to do is we were just trying to make a separate body by telling the slicer, making some insignificant change to the speed of the perimeters to tell the slicer to make the entire arm a separate body. Here, we're not doing that. We're not making a separate body per se. Instead, we're sticking a modifier in here and telling the slicer that we wanted to stick a perimeter on the outside of this entire modifier, which is what it's doing. Well, in practice, it's kind of splitting. What it's doing is it's creating a separate body. This modifier is only 1/1000th of an inch thick. As you can see, it's super, super, super thin. It is creating a separate body, which is that modifier, and it's trying to put an entire perimeter around that modifier. Now, that doesn't actually happen because that modifier is much too thin for the slicer to recognize as an actual part. So what we end up getting is the body of the frame. The two perimeters continue all around in the standard fashion, and then the modifier, which is acting, trying to tell it to add more walls around a body which is too thin to actually exist. All we get is we just get a thin gap, a little thin gap right here. So technically speaking, this wall and this wall not actually adhered together. It's just a thin gap. But in practice, the filament's so close, especially with TPU, it kind of sticks. And even if it doesn't, it still does exactly what we want it to do at forming a strain relief. In fact, this might even be better because it allows the layers to slide together, providing strain relief without introducing too much concentrated stress. So that's what we did there. In CAD, what I did to design this, we won't show you in CAD. We'll just stick to the slicer for now. I took the outer surface of this arm and translated it sideways. And we translated it sideways because the slicer is working in 2 dimensions at each layer. So you don't want to just take this entire surface and displace it inwards. And because of that, that's why we have this Gothic arch, so that every single layer line is, every single layer is the same, is what we're trying to get at here. We are horizontally moving the same distance with this modifier, and the end result is what you see right here. So that is how I reinforce the arm, and it's a cool little trick that hopefully this allows you to understand. Now, if you're anything like me, there'll be some miscellaneous questions you want to have addressed, so let me just do that now. First of all, how the circuit board mounts. We have a circuit board right here. Let's see, I actually have a few different circuit boards right here. We've been using a couple of these Happy model boards, both having overheating issues, moving to a little Beta FPV board, which seems more better built, but we'll find out how well it works. And the way these boards mount is we have these little mounting pegs in here, which the board kind of snaps into, sort of, into there, which kind of holds it in place. And then when this cover is put in place, the PA12 insert you can see it has these little tabs which snap in all around. So there's no adhesive, no fasteners at all. The only fasteners at all are basically the motor, the 2 screws for each motor, and the fasteners for the camera right there. That's it. There's no fasteners that hold the board in, which is super nice because it saves weight and it's very simple and makes it easy to install. Screws are kind of a pain, especially when you're trying to hold circuit boards in. So that PA12 insert right there, the top plate, you can see has this little overhanging section underneath. It has one of those in each corner, and it basically just holds the corners of the board in against those TPU posts and very securely holds that board in place. That's how the boards mount. Works super well. The battery contacts are a problem point right now. What they are is it's just a piece of that nickel strip which they use to solder batteries together, and you can see the batteries just snap in there like that, and they're actually super secure. I have not had an issue with any batteries coming out. It has happened a couple times during weird crashes and weird angles, but it's very, very rare, and never really on forward flight crashes. So it snaps in there. These little contacts, these little nickel strips, rely on the springiness of the TPU to hold them in place, and that works great during flight. I had not had any power outs during flight, but when you crash it, it jars it, and the battery disconnects for a second, and you lose your flight data, which is just a pain. And even if you're holding it and you smack it like that on the ground, it can jar the battery enough that you'll lose contact. So these little nickel strips, while they're homemade, they're a bit of a pain to bend. They're very lightweight, but unfortunately they're not going to work too well. You can see they go through slots in there. So on the recommendation of David from K9 Defense, I have ordered some proper battery spring steel terminals, which I'm going to slide in from the top here with wires which will solder to them and come out here. So similar, and that should fix that problem. That's the battery contacts. That's really, I think, the only details on it. The other detail, which might be interesting to you, which we addressed in our last video, is these wires right here. The motor wires are actually come through a channel which has been designed in the arm. So the wires are all totally internal, which makes for a really slick design. It works quite well. And then they're soldered directly to the board with no connectors to save weight, which is a slight inconvenience if you need to replace a motor, if it gets a broken wire due to hair wrapping around it. But that's pretty rare, so it's not a huge problem. That's about it for today's video. Hopefully it was pretty condensed, and I tried to explain just the highlights to show you what's going on with this project. I've been working on this now for quite some time, and I've been doing iterations slowly, not working on it too much, but I'm getting really close to a finished release. I just need to fix a few things, namely those battery contacts, trying to find an all-in-one board that actually works, that I can design it around, that doesn't have overheating issues, which I'm hoping that beta FPV one will be the ticket. We'll see. I've done a bunch of experiments with these boards and made some progress on fixing the issue and band-aiding it, but it's still kind of a pain, especially in really hot, like 85, 90-degree weather in the summertime here in Tennessee. So we still have to figure that out. And then, of course, the printability issue with the battery holder, it's a tricky process, and I got some glues and stuff. We're going to try to figure something out that's hopefully a bit more beginner-friendly. But stay tuned for this project. It's still in the works, and it's a lot of fun. You can cruise around for 20 minutes and never have to worry about smashing anything. And those propellers are almost indestructible, too. So it's a very liberating way to fly, as long as you don't fly into a storm drain or something. All right, guys, thanks so much for watching, and tune in again next time.